So we just spent a few minutes talking about how to build a hash table conceptually back there on the whiteboard. The next thing that we're going to do is we're actually going to build a hash table in C. And specifically, we're going to build a string-to-string hash table. Let's go ahead and open animals.c, which is going to be our test program for our hash table implementation. So we're going to print some stuff. We're going to have map.h be the interface declaration for our hash table. We're implementing a hash map. And then int main. Again, we're not using our command line arguments because what we're doing is pretty straightforward. So we're going to allocate a hash map called noises. And then we're going to go ahead and put some values into our hash table. So a chicken says cluck. And normally I would ask the class what noises animals make, but unfortunately I don't get to do an interactive lecture today, so we're just going to have to use standard animal noises. A cow says moo. An elephant says toot. A dog says woof. And a cat says meow. And I'm intentionally doing 5 animals because that makes sure that we're going to exercise the growing functionality of our hash table, because I think we start with a initial capacity of 4. And we're just going to start off with this as our test program. So we're going to insert this stuff into the hash table, and then we're going to figure out what noise does a cow make. And yes, this is a college course where we're talking about what noises animals make. So this is our test program. Next thing that we're going to need to do is we're going to need to actually build the thing. I'm going to start off by building our interface declaration header file, which was map.h. And header files in C define a public interface for some module in our C program. The module is usually implemented in a .c file, and then we define the interface in the associated h file. One thing that we do want to do in C is when we're typing in an h file, we want to do this thing, which is called an include guard. Because the way we include files into other files, the way we sort of import header files, is with the pound include directive, and the mechanics of the pound include directive with the C preprocessor are that it like literally inserts the text of the file into the file that it's being included into. We can run into problems if we do multiple includes of the same file, but if we do this this pattern of having an include guard, we can make it so that the first time this file is included, the contents is actually included, and on subsequent attempts to include the file, it is not included. Alright, so we need a map. Typedef struct map is a map. Now the contents of our hash map is going to be a bunch of, it's going to be a table of lists of pairs, a table of lists of pairs. So in order to do that, we have this is the array, and so this is going to store multiple pair pointers. And we're also going to store size and capacity, like in the diagram we drew earlier. So we need this pair type. And this pair type is going to have a char pointer, the key, a char pointer, the val, and then a next pointer, because this is acting both as a key value pair for the implementation of our map, but it's also acting as a list cell for the linked lists that we're storing. So pointer to array of list of pair. Well, saying pointer to is redundant for arrays, so this is an array of list of pair. All right, now we have our so this is the structures that we're working with. So next I'm going to define our interface function. So we're going to have a function map, make map. We're just going to allocate an empty map. And then if we have make map, we're returning a pointer. The caller of that function is then responsible for cleaning up that object. So we need to give them a function, in this case free map, that will clean up the corresponding object. So because we're dealing with a map of string to string, both the key and value type that we're dealing with are pointer types. And so these strings are going to be allocated somewhere. They might be allocated in the data section, they might be allocated on the heap, they might be allocated on the stack. But within our data structure here, if we want to actually be able to pass this other parts of the program, return it from functions, have it work as a map data structure, we really need it to have its own copies of those keys and values, which we know are safely allocated on the heap. And so this is going to when we insert an item into the map, we're inserting copies of the strings rather than keeping the pointers referencing whatever strings the user told us about. On the other hand, when the user calls get, we want to return a pointer to a string for them, but we don't want to make them be responsible for freeing that string. If they want to make a copy because they're going to store it somewhere, we can let them do that. But we're going to return an unowned reference. To the copy of the value that we made in the put operation. So in put, we make copies. In get, we don't make copies, we just return a reference. And so it's up to whoever calls get to not store a copy of, or to not store the pointer if they're then going to free the map. This pointer that's returned by get doesn't keep working longer than the map continues to exist. And it may not continue to work through deletion of that element. In fact, it won't work through deletion of the element. If we do map get and then delete the element and then use the pointer, it'll be a bad pointer. Next operation that we want to do is map del. And that's just going to remove an item from the map. And that's all we want for an interface for right now. There's more stuff that we want to have in our hash map, but this is sufficient for the moment. Now, we want to do one more thing here, and that is we want to go ahead and open up map.h, and we want to actually implement all of this stuff. And one thing that I like to do is to copy the header file over into the .c file. Now we're just going to include the header file to define these structs, but I do like to leave the definition of the structs here in the source file just for me to stare at while I'm typing things. So now we have these functions. Now all we need to do is fill in the bodies of these functions. And of course, I'm not typing this off the top of my head. So I'm going to bring up my notes. Alright, so in order to make a map, we need to malloc size of map. Then we'll return that. Then we need to fill in the fields. The fields are are data, size, and capacity. Now, size is going to be 0. We're creating this like make map function doesn't have any arguments, so the map that we make is going to be empty. But we do have to figure out what our initial capacity is going to be. And I'd like to make our initial capacity be 4. Because allocating an empty map isn't like, there may be cases where we allocate an empty map, never put any values in, and then delete it, and in that case allowing a capacity of 0 might make sense, but that's probably not the common case. The common case is probably that we're going to make a map, insert at least a few items, and then use it for stuff. And so if we do the allocation now, this saves a bunch of expansion. Also, 0 would be a special case. We can't double a capacity of 0, so we'd have to have an if statement in our grow function that would check for that 0 case. Calling malloc to allocate just one item is sort of silly, so 4 seems like a reasonable compromise. So this is going to be malloc capacity times size of pair pointer, because we're doing an array of lists of pair. But actually there's a trick. So malloc would work here, but there's another function that's worth looking at called calloc. And what calloc does is it allocates an array of items, and further it's going to 0 the memory. So the calloc function allocates memory for an array of n-member elements of size bytes each, returns a pointer just like malloc, but the memory is set to 0. And this avoids all kinds of uninitialized memory errors that we could have, or warnings that we could have otherwise, and just is nicer. So, in fact, it may even be reasonable to always call calloc and never call malloc. Calloc is an older function than malloc is in sort of the history of C. There have been arguments that I've heard frequently that I should teach calloc as the default instead of malloc, because you can always allocate one thing by saying it's an array of one thing. But malloc is the traditional thing that we talk about, and we're going to be talking about memory allocators shortly, where talking about malloc makes a lot of sense. So, in any case, calloc takes the number of members, so that's capacity, takes the size of each member, that's the size of a pair, this auto zeros things, so I like using calloc. To free the map, we're going to go ahead and iterate through the slots in the map. We're going to call free pair on each item. Now we don't have a free pair function yet, so we're going to have to build that. Let's go ahead and build free pair. And while we're thinking about this, let's go ahead and build make pair as well. So pairs aren't really a public, like, we have the pair type is defined in our interface, but we don't have any functions that operate on the pair type in our interface. We still need functions that operate on the pair type in order to implement our our hash table because it uses pairs. So we're going to create a make pair function. This is kind of like cons from Fundies 1. And this is just going to do malloc size of the pair. Then key is going to be stirred up of key. Val is going to be stirred up of val. Next is next, and then we'll return that pair. Now, stirred up is in string.h. So we're going to go ahead and include that so we don't get compiler errors. Free pair. So one thing that's going to happen is we're definitely going to get past null pair pointers. For example, down here we iterate through every slot in our table, assuming each one's a pair pointer, but if we call make map and then immediately call free map, then it's just an array of 4 null pointers. So this is going to skip things that are null pointers. So we can free null pairs all we want, and it's just not going to do anything. Then we're going to free the next one. If it's null, we stop. If it's not, we don't. We'll free the key and the value, and then we're going to free that pair. Alright, so we can make a pair, we can free a pair, we call free pair down here, back to free map. Once we've freed the pairs in the map, the next thing that we need to do is free the table, the array, and then we can free the map structure itself. Alright, next up we need our put function. So we are doing a hash table that handles collisions by chaining. Because it handles, and when I say handles collisions by chaining, what that means is every slot in the table is a list of pairs where the key in each pair in that list hashes to end up in the same slot in the table. But we still have a maximum load factor that we want to deal with. So here we're going to have a max load factor of 1.0. And if we get to a load factor of 1.0 and then we try to insert another thing into the table, we immediately want to grow the table. So I'm going to call map grow, which is just going to go ahead and do the grow operation of doubling the size of the table and copying the, rehashing every element in the table. So that's going to happen. So we're going to need that helper function. But we're more interested in the other case. So we're going to call our hash function on the key, and I'm going to implement my hash function so that it does the modulo operator automatically. So we're going to go ahead and pass in the capacity of the hash table. Then we're going to do an insertion into the front of the linked list. It doesn't matter what order the items in the linked list are. We know that it's a linear scan through the items. These linked lists are supposed to be short with a maximum load factor of 1.0. The expected length of sort of an arbitrary list in the table is going to be 2. So we have some, the expected length is 1, but a common length that we're going to see is going to be 2. The common lengths are 0, 1, and 2. Then we're going to do arrow size plus equals 1, and we've gone ahead and done our put operation. But we need 2 helpers. First helper is going to be map grow. this is going to take a map, and we're just going to grow it apparently in place. So we're going to store off the old capacity and the old data. Then we're going to go ahead and just mutate the array to have twice the capacity. We're going to allocate a new table, a new array, which is twice the size of the old array. And we're going to set the size of this table that we're working on to 0. So at this point, we have effectively allocated a new table in place over the old table, over the old hash map structure, allocated a new hash table over the old hash map structure with twice the capacity, an empty array of twice the size, and then the number of items in this table is now 0. But we still have the old array and the old capacity saved. So we can loop through all the slots in the old array and insert each one of those items in that, like the old copy of the table, into our new data array, into our new table. And of course, this is an array of lists, so we need a doubly nested loop to loop through all the slots in the array and all the items in each list. And this loop here will go ahead and skip any slots that are empty. So if the item in data II is a null pointer because there are no values, there are no keys that hashed to that particular slot in the table, we'll do 0 iterations of this loop, and so every call to map put is putting in one thing. Now map put is going to go ahead and increase the size. It could conceptually call map grow again, like it looks like it could, but because we are doubling the capacity here and only copying over however many items were in the table previously, we won't get any trouble with sort of recursive growth. We could probably even prove that if we really wanted to. All right, once we put a pair, we need to free that list, and free pair actually recursively frees the whole list because we've allocated new lists for the new table, and then we can free the old data array once we're done copying over all the pairs. All right, so that was put. The other thing that we need is our hash function. So the hash function is normally a function of the key type. In this case, that's a string, and it will produce an arbitrary integer. The hash function that we're writing has the modulo built in, so we're going to pass the capacity in here, and we're going to return hh mod nn. So this is this AND trick. So this assumes size of table is power of 2, turns hash mod size of table. So the hash I'm going to use is pretty simple. We're going to loop through the string, and then for each item in the string, we are going to take the old value in HH, multiply it by 67, and then add in the new item. This makes some sense. I'm not claiming this is a great hash function, but this is a plausible hash function for a string. The idea is that the string is going to contain sort of printable ASCII characters. That's what the items in the string are going to be. The range of an ASCII character is on the order of there are 26 characters in the alphabet. 26 times 2 is 52 for uppercase and lowercase. We also have digits, so that's getting to 62. Maybe there's some other characters. We're talking around 65 or 67 different values that we're likely to have for an individual character. 67 is a prime number that's around that size. So every time we insert another thing, this is going to fill in the low bits of HH, and we're going to mix it with the bits of HH sort of shifted over and shuffled by the multiply, and so this should sort of spread out the data in the string throughout the integer that we're returning. So then when we do this modulo operation, we get a random-ish string, or sorry, a random-ish hash number, random-ish slot in the array. So this works okay. It's worth Googling string hash functions to see how you can do better, but this is good enough for the example. All right, so that was put. Next operation is get. And yes, for this example, I'm typing in an awful lot of code without testing anything. I would recommend finding a way to test your code a little bit earlier than I'm showing here, because there is no way to write more than 100 lines of code from scratch and just get it right. It's impossible. Only reason I'm able to do it, appear to do it here, is because I'm copying from my other monitor. But yeah, next operation is get. And once we have get, we should be able to test. So our get operation, we're going to start by hashing the key. And here's a loop that you should recognize. We're going to loop through all the entries at that slot in the table. So by doing the hashing, we've limited our search to one slot in the table, but we still have to loop through all the slots in the table in case there were collisions earlier. And then we're going to say if strcomp, the key in the pair, matches the key that was passed in as an argument, and strcomp returns 0 if the strings are equal, or it returns -1 or +1, while it returns a negative or positive value depending on whether it's greater than or less than. In any case, we're just trying to do equality, so it'll return 0 in that case. We're going to go ahead and return that value, and in the event we don't find a match, we're going to return 0 just as our sort of indicator of failure in lookup. All right, so we're not going to implement delete. Now we're going to try to build this. To build this, we're going to need a makefile. So I'm going to write a makefile. I haven't talked about makefiles a lot yet. So a makefile is a place where we can specify the rules to build a C program normally. Really, we can specify the rules to do any sort of arbitrary task where we have input files and output files, or even where we don't. But most relevantly, we're specifying the rules to build a C program. So in order to build a executable called animals, the rule is we need 3 files: animals.c, map.c, and map.h. If any of these files change, then the program has changed, and so the animals executable needs to get rebuilt. if we want to build that file, the rule is we call gcc with debugging enabled. We're going to output a file called animals. We're going to compile together these two C files, and that's basically the whole rule. We're also going to have one more rule in here. If we want to delete, if we want to clean up our build directory, we can do that by simply removing this animals file. And normally a rule like this is going to specify how to create a file that may or may not exist. This clean rule doesn't create a file, so we want to mark it as phony, because that means that make won't sort of stop running our clean rule if for some reason a file named clean ends up in the directory. All right, now we can type make, and make, in fact, ran the command that we told it to run to build the file, and we started to get stuff. So let's go ahead and see what's over in map.h. This should be called make map. Over in map.c, malloc is in the standard lib.h header. All right, now we can type make again. So on map.c line 74, we say arrow value when the field name is val. Now we can type make again. We get undefined reference to make map. That's because this function that we're defining here is map. Make map. Make. All right, so we type make. It ran the compiler with no errors. The thing that make does that's sort of neat is if we run make again, it'll say there's nothing to be done. You haven't modified any of the source files for this program, so we're going to optimize the compilation by not doing it. Then we can go ahead and type animals, and we have written the most complicated set of code to print out the text, the cow says moo, that, I mean, it's the most complicated code to do that we've written for this class so far, but that was the test case that we were expecting to get to work, and it's only a couple hundred lines of code to do that. All right, let's complicate things up a little bit. So we're going to open up animals.c again. And we're going to delete that cow. And then we are going to iterate through the key value pairs in our map. And for each animal that we still know what it says, we're going to print out the name of the animal and the noise it makes. To do that, we're going to have to implement this Iterator interface, which is a little bit tricky, but if you're used to C++ or Java, it's sort of neat to see how we can build something like this iterator. And we kind of need to for this data type, because the structure is complicated enough that we would have to have an awful lot of like doubly nested loop to loop through both the array and the lists in the array every time we wanted to do a traversal. So the iterator is useful. All right, so back in map.h, we're going to need that map it structure. Which is slightly more complicated than it looks like it should be. We're going to include our map. We're going to have a II is our current position in the iteration through the array, and then item is our current position through the list. And both of the two pointers are unowned references. We're not making copies for the iterator. These reference an existing array, or sorry, an existing map. If the map is deleted or mutated, then that invalidates our iterator, just like iterators in sort of OO languages. So our iterator interface is 3 functions. Iterate constructs an iterator. Has next is going to tell us whether or not there's another item to iterate through. This is our termination condition. And this returns a Boolean, which in C is spelled int. And then finally we have our next function, which is going to take an iterator and move it forward by 1. Alright, so then over in map.c, we're going to go ahead and implement that iterator, and implement our deletion. So deletion is pretty straightforward. All we need to do is determine what slot in the table our pair is in. And then we're going to go ahead and the lists within a slot are basically association lists or A-lists. So we're just going to call out to a helper to do the actual deletion from the list. So this is going to take a pair pointer, because we want to be able to do a deletion in a linked list, which means we need to be able to go back and mutate the reference to the pair that we're looking at. So, and we want to know which key we're deleting. Now, the thing that we are currently looking at is the thing that our reference references. And then if that is non-null, so if they are equal, we're going to delete. If they're not equal, we're going to keep going. Actually, we don't even need to have this be an else case, because it's conceptually possible that we could have screwed something up and implemented, like, inserted the same key twice, but we probably didn't. But it's not worth having extra code in there to sort of avoid the case where we inserted something the same key twice by mistake. Alright, so there's our deletion operation. Next thing that we want to do is the iterator operations. So creating the initial iterator is pretty simple. The map references the map. I is 0. The item that we're looking at is the 0th slot in the array, which may or may not be empty. And then we're going to return that iterator. Now, for this hasNext thing, we're going to cheat a little bit. We're going to actually just call the next function and then ask if the item is null. Because when we eventually get a null item from next, that means we're done. All right, so this is the complicated one. So if we have an item, we're going to go ahead and move to the next item. But that might be null or not. If it is null, that means we're done with the current slot in the array, and we have to start iterating through the list. So this is always going to move forward until it finds another non-null item, until it gets to the end of the whole data structure, at which point it's going to return an iterator with a null thingamadoozy. Now there is a potential bug in this iterator. If you spotted it, great, but we're just going to go ahead and see if this works. Right, alistdel has parens in the wrong places in its recursive call. Now it compiles. Okay, so the cow says moo, the dog says woof, the elephant says toot, the cat says meow. What happened to the chicken? Good question. And in fact, I think what I want to do here is leave what happened to the chicken as an exercise for the student. So good luck getting started on your hash table. Here's a partially working example to work with. And yeah, I'll be back with more of this week's lecture. But this hash table stuff is the stuff that is of some use for the upcoming data structures homework.